So in this lecture we will consider one more application of the methods which we have developed. So let us start from motivation. And motivation is the following. As most of our examples go, we will consider some problem of quantum mechanics. And now let us discuss again potential scattering in certain potential u of x, which is described by the Schrödinger equation. And just to have some specific example in mind, let us draw some tentative shape of u of x. And there is a certain class of problems, important class of problems in quantum mechanics, which is called overbear reflection. And it is this problem is formulated like that. Imagine that you have a certain potential which tends to constant limits at x plus and minus infinity, and we know from the standard quantum mechanical course that and from the form of this equation, it's easy to guess that at x going to plus and minus infinity, wave function becomes, so as long as u of x goes to constant, and this constant can be chosen to be 0 without any loss of generality, we understand that this equation becomes a very simple one. And in fact, this equation, of course, can be easily solved. And if we imagine that energy is positive, this, of course, means only that energy is higher than long distance asymptotics of the potential. So in this case, the equation can be easily solved. And it has two linearly independent solutions. It is just an exponent which is propagating to the right or to the left with wave vector determined by the equation itself. So it's actually for the asymptotics of this equation, the solutions are simple. So in principle, if we have some particular solution of the equation of that kind, we understand that its asymptotics to the right should be some linear combination of two asymptotic solutions. And its asymptotic to the left should also be some different combination of the same asymptotic solutions. And there is a certain class of problems, which are problems about reflection in quantum mechanics, in which we additionally restrict ourselves in considering some special class of solutions, which corresponds to the following figure. That to the say to the left you have one incoming wave and one outgoing wave, and to the right you have only outgoing wave. So this is the same potential with constant limits at infinity. And here you have some, let us now use some other notations. So let us call this t, to be consistent with quantum mechanics, let us call this t time exponent of I kx. Here we choose a certain normalization of the solution and choose coefficient 1 here. And this reflected wave is r time exponent of minus I kx. So to be more formal, we just solve this equation with the following asymptotic boundary conditions. So mathematically, this problem is formulated as simple as that, and physically, it also has a quite straightforward interpretation. This wave to the left corresponds to incident particle, which is normalized to the flux k, and there are two waves scattered from the potential. One scattered to the left, and another is transmitted wave with amplitude t. So and this t and r are called transmission and reflection amplitudes correspondingly. And our problem will be to study how these coefficients can be evaluated. And before we proceed, let us note that this problem is as soon as energy is higher than highest point of the potential, this problem makes sense only in quantum mechanics, but not in classical. Because imagine that in classical mechanics, you try to pass through the potential barrier with energy higher than largest value of the potential itself. Of course, it means that it will be fully transmitted. There is no reflection. And only in quantum mechanics it becomes possible to scatter from the potential even when you bypass it at energy which is higher than highest point of U of x. And this is a phenomenon called over-barrier reflection. And in this lecture, we'll discuss how to calculate the corresponding transmission coefficient, reflection coefficient, and how is this problem connected to everything we have discussed so far. So in this lecture, we will discuss what kind of tools do we have and how to apply what we have learned in order to solve this class of problems of over-barrier reflection. So, and of course, this problem belongs to a general class which is called a wave-like equation. And the simplest wave-like equation has the following form. So imagine if k is constant, then of course this equation has two linearly independent solutions, as we have just discussed. But the Schrödinger equation with potential which is x-dependent, which is position-dependent, does not reduce exactly to that kind of equation. In fact, in Schrödinger equation, this wave vector is position-dependent. And obviously, this kind of solution is not valid anymore. But as you may remember, in one of the previous lectures, we have discussed the quasi-classical approximation, in which the solutions, two linearly independent solutions, are approximated by the following expression. And one of the most important points in the analysis of these solutions was that it is not valid in the vicinity of certain special points, so-called turning points, in which the wave vector becomes 0. And in this case, the equation becomes essentially quantum mechanical and cannot be treated quasi-classically. But these points are determined by the vanishing of the velocity of the particle. And let us see what does it imply for the over-barrier reflection situation. So imagine that we have the potential of that shape, U of x, and with certain height u naught, and our energy is, as we have discussed, higher than the peak of the potential. Let us try to apply this quasi-classical formalism for this reflection problem. And obviously, we are looking for the solution which is incident from the left. It means that we can try the following shape of the solution. This boundary condition simply means that we need to write a wave which becomes propagating to the right only to x, with x going to plus infinity. So naively, we should just write exponent of I, and proper choice of sign here is dictated by the fact that particle propagates to the right at large positive x. So it means that we have to choose plus here. And very naively, this solution, although approximate, is valid everywhere. Why? Just exactly because this condition, when this solution breaks, requires existence of some special points, turning points on the real axis of x. But obviously, there is no such a point in this situation. So it means that wave vector calculated as doesn't vanish anywhere on the real axis. And this could lead us to the conclusion that this solution is valid everywhere. And of course, we should also as well propagate it to the left, which means that there is no backscattered wave to the left of the potential, which is of course contradicts to our initial understanding. We do expect in quantum mechanics to get also the wave which is reflected. And this is looks like a paradox, but in fact it's very easy to resolve it. And the simplest route to realize how this paradox is resolved is to take a look at exact properties of k of x. And in fact, we understand that although k of x doesn't vanish anywhere on the real axis, it does, of course, vary. And it becomes smallest somewhere when the energy is closest to the potential. So it means that somewhere in the vicinity of the top of the hill of the potential, the quasi-classical approximation works, but not so good anymore as it does far from the hill of top of the potential. It means that somewhere in the vicinity of this point, the quasi-classical approximation can be expected to break down. And in fact, this specific point where it does break down can be found, say, formally for now, by solving the same equation. But look, we have just discussed that this equation doesn't have a single solution, and now we're trying to solve it. And the resolution to this paradox is, of course, simple, and in fact, we just need to go to the complex plane. And as we will see momentarily, although there is no turning point on the real axis of x, there is actually turning points with x being imaginary. And with analysis of these so-called complex turning points, we will start our discussion of the methods to solve this kind of problems.